6.4 Essential question. Can I use integration to find the total work done in a system? Work is done against gravity when lifting an object. When you lift it in feet and the force is pounds, work is foot times pounds or foot-pounds. When the distance is meters and your force is in newtons, that's going to be newtons times meter, the unit of work is called joule. If the force is, if you have the mass and acceleration, you can derive the force. This is from Newton's, one of Newton's laws of motion. And so m stands for mass, and acceleration in calculus is the second derivative, which is this. And when you take those two quantities, multiply them together, that is what newtons is called. And again, when the force is in newtons and the distance is meters, we do get joules for our work. Let's talk about something that doesn't require gravity. Let's talk about compression and stretching of a spring. There's something called Hooke's law. Hooke's law says that the force is dependent on the spring constant and the amount that you stretch it or compress it. The more you have to do, the more work is associated with it, because that's a linear relationship right here. Let's do some problems where we have to find the different information. So we're being given a spring constant. I put that into the K. We're given the amount of stretch, and you notice I had to turn it into meters, and then I got my force. Over here I have my spring constant. My units of stretch is already in meters, so I just have to multiply those together and I get my force. In this last problem, I'm being given the amount of stretch and the mass. Mass isn't a force, so I have to go here to F equal to MA. I'm going to change my mass into kilograms. I'm using acceleration here, and then I get my force in newtons. I go ahead and put that force here. I have my stretch, and I convert it into meters, and then I'm able to find my spring constant. So why is this a good problem for calculus? Because if we want to find the total work being done and not just the work to one distance, and we want to find the work over the whole thing, then that is going to be a variable force, and it's a perfect application for calculus. What we're going to do is we're going to treat each little movement from here to here as if the force is nearly constant, and therefore we can use that force times distance idea, force times distance. So at every little interval there's going to be a different force, and it's going to be over that little interval. I'm going to sum up all the works and take the limit as the width of each of those works is going to 0, and I'm going to get an integral. And so in summary, here's how we do work. Force times distance. And this force, because it's a spring, will be K times X. All right, here is an example of a problem. Notice that this information right here is to help us find our spring constant. Once we find our spring constant, then we have an expression for our force. We can then describe the force in a Riemann sum, force and distance, and then set it up in an integral. All right, your turn. Stop the screencast and see what you can do. And here is the answer. Now let's talk about work in a non-calculus physics course. We want to figure out how much work lifting this amount of mass to this many meters. Well, if this is mass, remember we got to convert it into force by multiplying by gravity. And then we have our force in newtons. We're going to take our force and multiply it by the distance, and we're going to get our work in joules. Now, suppose part B says the work is in pounds. This is in a different unit, and pounds is already a force, so you can already put it into for F. And then the distance is in feet, and we get 120 foot-pounds. All right, here's a problem where the force is varying. Here's the force is varying, so we do have a function where we can go ahead. This is our force. This is our little distance for every little bit of force that's being acted on it. and then we get our answer. Oh, okay, let's talk about a 200-pound cable. It's in pounds, so already our force is there. A little piece of work will be done from here to here, and it's going to be a little distance, so we're going to assume that the force is nearly constant. That's why we can use this force formula. Now, I do need to, the force is varying, but it didn't give me a formula. So I'm going to go over here. I know the formula is linear, so I'm going to set up some data here for me so I can look at it. When x, this length right here, is 100, it has the full force of the cable, which is 200. When the cable is only half hanging down, which is 50, then the force that's required to lift that part up will be 100. And of course, when the cable's all the way to the top, there's no force. Now this is a linear relationship with a point 0, 0, so I know it's an mx kind of force. And if I look to find my slope, I'll see that my slope is 2x. So now I can go ahead and write 2x for my force times delta x. And then I can set up my integral from 0 to 100, because that's what the x's are going to go from, 0 to 100, and it'll be 2x dx. And if you go ahead and put that in your calculator, you're going to get 10,000. And again, this part right here is feet, and this part here is pounds, so it's foot-pounds. Now let's take a look at another problem, a tank, and it's inverted cone, and we're trying to find the work to take all the water out over the top. So a little piece of work is going to be the force that's required to take this water up, and the force to take this water up is changing all the time. And again, there's some kind of relationship with distance, how far it has to travel up. Let's go ahead and talk about the distance it takes for a little piece of water to travel up. It varies depending on its position. So if I have this point as the starting point at 0 and this part is 10, the distance for this water right here at the very end is going to be 10. And the distance for the water up here at the top here will be 2. Now since I have 0, 10, I know I have a plus 10. mx plus b, I have my b already, and I just have to figure out my slope. And if you go ahead and figure out the slope, you'll find it's -1. And so here is the relationship for distance, which I could say 10 minus x. So now I have a relationship for distance. Now the force is going to be mass times acceleration. Now mass will be comprised of volume times density. That'll create my mass. And my mass is a cylinder. This is the cylinder. Pi r squared delta x. This is the little delta x, and this is the r. And then the density, remember this is going to be cubic meters, and the cubic meters are going to cancel here, and I'm going to have kilograms eventually. And then I want to times by my acceleration. So if I take all of this and multiply it, I have here. Now here's the problem. When I integrate, I'm going to integrate with respect to x, and I have an r here. So I need to figure out how r relates to x. So I'm going to go back here, and I'm looking at a triangle right here, two triangles. This is back to geometry, and you can see that these are similar triangles. This is 4, this is r, this is x, my height, and the total is 10. So the sides are in proportion. 4 is to 10 as r is to x. So r is equal to 2/5 r. So I'm going to be able to replace this r with this quantity right here. All right, now I'm going to go here, and I'm going to now have a way to write my force. So that's 9,800 pi, and then I'm going to replace my r with 2/5 x quantity squared, and I'm going to move this delta x out over to here, and I'm going to put my distance formula that I just figured out, 10 minus x right here. So here's an expression for my work. And to get the total work, I'm going to integrate. And remember, my x's are going to go from 0 to 8, not 0 to 10, because there's no water between 8 and 10. So this is going to be 0 to 8, and then I'm going to have 9,800 pi times 2/5 x quantity squared, 10 minus x dx. And when I put that in my calculator, I'm going to get about 3,360,000, and that's work, so it's joules.